Welcome back, everybody. Rolling through our amazing agenda of afternoon sessions here. I'm so excited to call Rick Houlihan to the stage. Rick leads our developer relations team dedicated to strategic accounts. He operates as a technical leader for the global strategic account team, where he was responsible for building the market for MongoDB technology by facilitating creation of similar center of excellence capabilities within our customer organizations. And these are based on principles that he's established throughout his career. He brings over 30 years of technical experience to MongoDB team and has authored 9 patents. Please welcome Rick Houlihan.
Great, thanks everybody. Thank you for braving the weather and taking the time out of your day to come hear me talk a little bit about a topic I'm a little passionate about. My name is Rick Houlihan. I'm the Director of Developer Relations for Strategic Accounts here at MongoDB. I was formerly the worldwide technical leader for NoSQL services at AWS, and I led the black belt team for NoSQL technology for Amazon Retail. For those of you familiar with Amazon's Rolling Stone project, we called it. It was the deprecation of 3,000 Oracle Server instances and the migration of thousands of workloads from RDBMS to NoSQL. And my team was responsible for establishing the best practices and defining the design patterns and whatnot that were used by Amazon Retail. And a lot of that is actually what I brought to MongoDB today. I'm not getting any reaction here. There we go. So what we'll talk about today is a little bit about why Amazon made that choice. So initially it wasn't all about, let's move away from the relational database, right? It was really just get away from Oracle. We had a lot of reasons for doing that we'll talk about in a few minutes, but no enterprise makes those decisions for no reason, right? And they're really good reasons, and they're financial reasons. So that's what I like to talk about a lot, because a lot of times that's the question I get. Why should I use NoSQL technology? And I'll tell you why you should use it, because if you want to stay in business, you better be thinking about it. And we'll break down the reasons why. I'm going to talk about how we went about that process. What were the, not only the reasons for doing it, but some of the method that we went through to determining, what needed to be done and why it became, replace the relational database instead of just move away from Oracle, which was the first mission. A lot of it is about modeling data, right? How do you model data in a NoSQL database? The difference between modeling in a relational database and a NoSQL database. It's kind of interesting. All data is relational. We can't, as developers, I think this is where developers break down a lot when people talk about non-relational data, right? Usually someone who's talking about non-relational data is somebody who's non-technical. Because if you're writing queries for the data, it's the conditions of the query that kind of define the relationships in the data. And we better be able to model those relationships efficiently, or we're not going to be able to use the database. It doesn't matter what database it is. So I like to say there's no such thing as non-relational data. That's actually the data that's on the hard drive before you format it. It's the noise in the air between the static in the air between the channels of the radio, right? That's non-relational data. Things we don't care about. If you care about it, it's relational. So we'll talk a little bit about that. And then we're going to talk about what it was like to execute the plan, right? Migration at scale. How do you get an organization of 25,000 plus global developers at the time and get them marching to the beat of a new drum, right? What does that process look like? And that's a lot of what I do today. So the first thing we'll talk about a little bit is why did Amazon make that decision? And to understand why, we need to understand the business a little bit. A lot of people think Amazon was born in the cloud, but it was not born in the cloud. It was born in 1995. The cloud wasn't even born until 2005 when the first EC2 instance was launched, and that's actually when Jeff sent out his famous missive to all of Amazon Retail and said everything from henceforth will be service-oriented architecture, right? So up until then, we were actually just like every other enterprise in the world, built on monolithic stacks, okay, legacy technologies, and we were a $5 billion business before we shifted to SOA, right? And actually what's interesting about that was, turns out that was a harbinger of what was to come, right? When Amazon was one of the first enterprises to actually go all in on service-oriented architecture, or look at us today. What enterprise today is not building on that? So if you look at what Amazon made that decision in 2005, they made another decision in 2017, right? By 2018, the scale of Oracle was breaking everything. And it was actually quite embarrassing to sit up there on stage at reInvent, talk about our wonderful database technologies, and then have Larry turn around 2 weeks later or whatever at the Oracle conference and say, hey, if it's so great, why are they my biggest customer? And that was a real problem. So this was actually the mission when we started. It was get rid of Oracle because we're tired of hearing Larry talk about how great Oracle is, right? And so the idea was we're going to take everything, we're going to just lift and shift this stuff into RDS instances. We had Postgres RDS, we had Aurora, MySQL, and we were going to just move all that stuff. We were all SOA, right? At this point, not really. We had plenty of legacy apps as well. But the idea was we'll just move this stuff into RDS backends, and we'll get rid of Oracle and stop that needling. We had the largest Oracle Server license at the time in the world. We had the biggest Oracle rack deployments, 3,000 Oracle Server instances, 10,000 application services deployed across those instances. Again, 25,000 plus developers, all working with an RDBMS first mentality. But the cost of that relational database was a huge line item, right? It was something that the business did not want to bear anymore. So we had to find a better way, right? That was the mission when we first started, again, was replace all that stuff with Postgres and Aurora MySQL. But what's interesting is when you look back at history, and the history of data processing is no different. The history of data processing is about what I call a series of peaks and valleys in data pressure. Okay, data pressure is the ability of the system to process the amount of data that we're asking it to process at a reasonable cost or in a reasonable time. Right? When one of those dimensions is broken, we have a technology trigger and we start inventing things. And we've invented many things through the years, right? We weren't born with the relational database, actually. We were born with the great database. It's the one between our ears, right? It's highly available. When my eyes are open, it's online, okay? But it's a single user system. It's got questionable durability, has zero fault tolerance, right? We're not going to build enterprise services on this. So we invented something. And what did we invent? Ledger accounting. We just started writing things down. What's the definition of a database, right? A system that is designed to store structured data. Okay, well, there you go. For many millennia, we ran public and private sector enterprise until the 1880 US Census, when a man named Herman Hollerith was tasked with processing all of that data, and it took him 8 years of that 10-year cycle, right, to process the data. And he realized it's too expensive, it's too slow. We're going to have to invent something. He invented the machine-readable punch card and the punch card sorting machine, and the era of modern data processing was born. Right, we started pushing the edges of that technology very quickly, started inventing many things, right, paper tape, magnetic tape, distributed block storage, random access file systems, hierarchical management systems, and eventually, in the late 70s, early 80s, arrived this wonderful thing that we still use today, almost 40, 50 years later, the relational database. Okay, it's important to understand that the relational database was invented by a man named Edgar Codd, who himself did not believe that this technology would ever be suitable for high-velocity OLTP applications, for transactional workloads. Why? Because it was too expensive. It would cost a lot to join those tables, and the CPU was the most expensive resource in the data center in 1975, 1980, when they built System R. But what Edgar Codd wanted to do was he wanted to build a system that allowed people to ask questions of their data without having to write code. Okay, what he was really trying to solve was analytics, the problem with data analytics. Everyone had to write code to write a query in 1975. He wanted a system that allowed people to be able to run ad hoc queries. So they invented System R, and the relational database was born. But every critic said, yeah, it's a great system, Ted, but it's not going to be suitable for wide-scale deployment outside of analytics because why? It's too expensive. But this little thing called Moore's Law, right, came along. And Moore's Law lessened the pain for many years. We're going to break this down in a second. But Moore's Law made that pain go away. It didn't make it actually go away. It just made it less noticeable, right? It's like a sore back, When you're 20 years old, it doesn't matter. When you're 30, it starts to hurt you. At 40, 50, like me, you go, oh my God, I don't want to get up in the morning, right? This is what happens with the relational database. So if you look at what's been going on for the last 40, 50 years, it really stopped in 2014. What I love about this is if you look at the chart on the left, it's not about database technology. This is processor efficiency. Okay, the top 500 supercomputing clusters in the world have been unable to meet Moore's Law performance gains since 2014. That's almost a decade. Okay, they have not been able to do this consistently. And if anyone's investing in the technology to be able to boost the CPU efficiency of their system, it's the top 500. Right? Every petaflop matters. They all want it. HPC is demanding of the most high-end processing technology. And you can just see what happened. It fell off a cliff. Right? Processor performance, per thread performance, power consumption per core, it's all flattening out in the CPU realm. And why is that? Because guess what? The 5 nanometer CPU is too expensive. Right? Moore's Law is not a law, it's a financial equation. How much is the industry willing to pay to double transistor density every 2 years? And right now in the server processing space, not enough. Okay, where you're seeing it is here, mobile devices. Why? Because this is a loss leader. Everyone knows what you pay for this is a fraction of the cost of the system. But I get 5 years worth of subscription services when I get somebody into a cell phone, so obviously that's where they're making their money, not on the hardware. Server processing space, no such luck. You don't get someone to subscribe to services when they buy a server, piece of server hardware. It's a pizza box that goes in the data center. Last thing I want to hear about is charging me monthly. Nobody's going to do that. So the server processing space is not seeing that kind of performance efficiency anymore. However, storage is continuing to fall. So what you're seeing is where Moore's law used to kind of keep the equation together, we're seeing a separation now. And this separation is happening, and it's not something that I'm telling you. This is something that the man himself will tell us. Okay, this is Edgar Codd. This is the words that he wrote in the seminal paper, right? A relational model of data for large shared data banks on normalization. You gain in storage efficiency from deduplication of the data. You can gain in bulk transmission of data across systems, but denormalization is going to reduce the time complexity. It's going to increase the efficiency of your CPU for some queries, he says. Well, it turns out that some queries are actually the ones we care about because OLTP workloads are the ones that run at high velocity, right? OLAP workloads don't. So again, not my words. He even talks about the cost of normalization on defining the ERD down there in the lower left when he talks about don't join in tables that are full of immutable data, right? And we see it all the time. How often do you see the events table with 10 rows or not even that, 5 rows, right? Event states, info, critical, warning, error, and I'm joining it in every single time. We don't care about this stuff. We don't think about this stuff, but it's CPU ticks. Okay, and this is really some of the things that we started figuring out when we were at Amazon. Those CPU ticks become expensive when you're talking about applications that run at scale or thousands of services that are running together, right? Bottom line is, when you say why NoSQL, when NoSQL, it's really about OLTP workloads, right? NoSQL databases maximize the efficiency of your well-known access patterns. OLTP workloads are hard-coded. Those queries don't change. They don't ask thousands of random queries every day. They ask the same questions millions of times a day. So if I optimize the data model to support those queries, I'm going to have a better experience, right? I'm going to need less infrastructure to support the workload, and it comes out to a lot less. We'll break this down in a second. SQL databases, on the other hand, are really good at OLAP workloads, right? Where you can ask ad hoc queries. I don't really care the questions. As long as I have an SQL API, I can support those OLAP workloads, and that's a good thing for NoSQL databases because today it's not about NoSQL, it's no RDBMS, right? And we're going to break down why in a second, but all NoSQL databases, not all of them, but many of them, including MongoDB, support SQL read APIs that'll be more than happy to satisfy those OLAP workloads and those OLAP queries. I would be the first one to tell you we're not going to do it as efficiently as the relational database, but I'll also tell you you don't care because OLAP workloads don't run at high velocity. They don't typically they're not latency sensitive, right? Who's running these queries? Right? This is typically maybe end of day report, end of month, end of week, an analyst coming in because something crazy happened yesterday. He's writing an ad hoc query, support desk guy. What do they need? They need an answer. Do they care if it comes back in 10 milliseconds or 100 milliseconds? No, they don't. But I'll tell you what, that OLTP workload sure does. So let's talk about what do you want to optimize of these two silos? You really want to optimize the one on the right. Okay, the OLTP workloads that run thousands and millions of times a day, those are the queries that are going to cost you. The ones on the left, those are pennies. The ones on the right, those are dollars. And this was a big lesson when we were at Amazon. So when we came down to it, if you want to make it work, it's about relationships. Okay, got to be able to model the data. We talked about this just a minute ago. If I can't model the data efficiently, I can't use the database. Okay, and this was a big lesson. It didn't matter what application you're building, social networking, shopping cart, document management, IT systems management, everything is about relational data. We need to be able to model those relationships efficiently, be able to use the database, but it's the access patterns that drive your cost. Okay, this is where everything changed. When Werner started breaking things down and we saw that 70% of the access patterns across all those 10,000 services we run hit a single row of data on one table. Okay, 20% more hit a range of rows on a single table. Why? Well, because it's OLTP workloads, and those are very write-heavy, right? A lot of times in OLTP workloads, the data is written and never even read, right? It's just recorded. Sometimes it is read, but it's not read in complex ways. It's read, again, as a single item on the table. So a lot of your reads are for a single item. All of your writes are for single items and range of items. So this is where he sat there and said, well, look, if we don't need the complex queries, then why don't we look at NoSQL as a solution? And the black belt team was formed, and we went charging down this path, and my team started going down and finding out that the devil's in the details. What it came out to was about 50% of the infrastructure requirement was for the last 10% of those access patterns. Why? Because that's where the joins were, right? That's where the complex SQL came in, and it's actually what made everything work, okay? Those complex reads, complex joins, we need to have those things. We need to be able to support those things, or we can't use the database, right? And this is exactly what happened when teams started coming back and talking to me about NoSQL, right? It came down to a modeling exercise. Today, when we model things relationally, this is how we do it, right? We've got a product catalog here. It's a simplified product catalog. We've got 3 types of products: books, albums, and videos, right? One-to-one relationship between products, books, albums, and videos. We have a one-to-many between albums and tracks. We have a many-to-many between videos and actors. All the types of joins you might expect to see. And if I want a list of all my products, I could have 3 different queries, right? Various levels of complexity. It's not even really all that complex, but we'll break it down in a second. The reality is, though, if you think of a product catalog, what is the access pattern? It's get product by ID, get product by type, maybe, get product by category, ranked by cost, or whatever. But there's always, it's very product-centric. Typically what I want is I want the objects that represent the products. I want all of those rows. I don't want to have to join those rows every time. So what I'll end up doing is I'm going to stack something in front of this thing, maybe some sort of cache, so I don't have to, I can offload the pressure on my relational database and not have to do all those joins, because joins are expensive, right? So I'm caching the results of the queries. Again, more complexity. Now I got to deal with cache invalidation, cache synchronization. I have all these problems that as a developer, why do I want to worry about this? That's not my business, right? The business is selling products, not managing cache consistency and dealing with all this huge complexity in my application layer, right? So maybe it's a better idea to store the data the way the application uses it. In this particular case, absolutely. Pre-join the data into document structures with embedded subdocuments, because that's always how I'm looking at getting the data. But what's important to understand is that applications don't always use data this way. Right? A lot of services do. This is good. This is a good data model for a lot of services. But many applications actually use data in bits and pieces. If you think about it, 70% of the access patterns are for a single row of data and 20% for a range of rows. That's cluing you into something. All those rows, they belong to these giant relational structures, but they're being accessed independently in small bits and pieces. This was a real clue when we started breaking things down at Amazon and how we wanted to model the data. But when you break down the time complexity, it becomes really apparent what's going on here, right? What we want to do, in this case, let's load some data onto these tables. Let's look at the SQL. And look at the time complexity down below. Now you can all tell me, yes, but Rick, it'll all reduce to O log n, and yes, it does, but that doesn't eliminate the fact that there's CPU cycles that need to be counted for as we go through these joins across these tables, right? So the one-to-one, not too bad. One-to-many gets a little worse, right? Many-to-many gets even worse. And it's in this case, if you look at this SQL, a DBA that's familiar with production SQL is going to look at this and say, yeah, I haven't seen anything like that since, right? I was just learning about the relational database. This is simple stuff, but it drives the point home. If you actually had complex SQL, outer, inner stuff, derived tables, joins on derived tables, imagine what the time complexity is going to look like. It's going to be tremendous. It's going to be horrendous. The other side of the coin is to actually look at the model join, the cost of model joins in NoSQL. I'm going to show you 2 types of joins here: an embedded join and a distributed join. People say we can't join in NoSQL databases, but I'm going to show you how and how to do it with a lower time complexity. With a model join, what we're doing is we're taking a document. We're going to embed some of the data that's interesting here. If you look at this document structure, we have a data blob. The data blob is like a property bag. That's like the properties of the product. In this case, the book, I've got the price and the ISBN. I might have a dozen other attributes in there. I'm really not interested in those attributes. I just want to get them, right? What I'm more interested in are the things it's related to, right? The product ID, that's our main access pattern, get product by ID, right? Get product by book title. Time complexity O log n. It's an index lookup. But what's interesting here is if you look at this document, this target array, these are pointers. What else is this document related to? Again, access patterns typically they use data in bits and pieces, right? They don't use data in big, large chunks. And we need to be able to represent that data in bits and pieces. So maybe I need to update small bits of the relationship that the book has with other things, right? I don't necessarily want to embed the book in the author document and update the book along with every other book the author's ever written. That's going to get expensive. So in this case, what we're going to do is just decorate these objects with pointers to other documents that they're related to in this collection, and then we have simple product documents that describe the data that we're most interested in when I go get the product by ID. Right, here's a list of songs that it's related to. I've got some data that describes the album. We've got, again, select for the movie, right, the many-to-many join. Again, time complexity, log n. All I'm doing is this key value lookup here, right, get product by ID. But what's more interesting now is when we start adding more dimensions, right? Like I said, data is used in bits and pieces, but it's all parts of bigger relational structures. So in this case, maybe I want to get all the movies an actor was in. I want to get all the movies that were directed by a given person, or the author, all the books that an author wrote, right? All the musicians that played a song. I can decorate all these things. I can put all these entities in the collection, decorate all these objects with pointers to each other, and when I index the target arrays, right, those pointer arrays, one of the most powerful features of document database modeling is multi-key indexes, right? Being able to take those arrays and create multiple entries on the B tree for each one of the pointers in those arrays. And if you look at what's happening here, if you think about what the relational database does, right? The relational database at its core is responsible for joining indexes. That's all it does. It takes an index on the parent table, an index on the child table on a shared dimension, and it joins them, it merges them. This is where the time complexity comes in. If I have one collection, I put all those rows as document objects in one collection, and I index a common attribute that's shared across all those objects. Essentially, the index is already joined. It's not, I don't need to join it anymore. So now I can say, hey, select where the target ID equals Mary Shelley. I'm going to get everything that she's related to. I could filter it on, everything that she was the author. Give me every person she's related to, right? I could do the same thing for any entity in this collection. Get me everything where it's targeting a particular song name. I'll get all the musicians that performed it, the albums that were recorded on, the studios that recorded it. Whatever I want to link to that thing, I just put it in the target array of one of the documents that it's related to. And look at the time complexity. Again, O log n. All these joins. They're not really joins. They're just index lookups now. We've eliminated all of that extra CPU that's going and hopping around trying to get this from that table and this from that table and merge all those lists together. And we replaced it with single index lookup. And even when we go down to the movie, right, all the way down to the many-to-many, that was the big, heavy one at the bottom of that other chart. I can say, give me everything where the target ID is a movie title. I'm going to get all the actors that were in it, the director that directed it, right? I'm going to get the movie object itself. Essentially, one request, it's a pre-joined result set, right? So essentially, by putting all the objects or all the documents in one collection, I'm going to allow the indexes to essentially perform the join operation, and I'm going to reduce the time complexity of my most complex queries to O log n. This is how NoSQL databases are going to save your money, right? When you look at what's happening, we talked about processor efficiency is just flattening out. Storage cost is decreasing, right? The lines of those models are separating, right? The cost of relational database is not getting any cheaper. This is exactly what was the math we looked at Amazon. Why did we make the move, right? Because we're saving an enormous amount of money by going down that road. As a matter of fact, I talked to the teams these days that executed that migration, and the people that I'm talking to on what they call the Plus team now at Amazon Retail are telling me that the service teams that migrated in 2018, 2019 have grown 3 to 4x their size, and they're running at the same level of database infrastructure costs as they were in 2018. Okay, so they grew for 3 or 4 years, they've tripled their size, quadrupled their size, and they're running at the same level of cost. This is why it's important to understand that a relational database, it's yesterday's technology, okay? And for the same reasons that we have made the decision over and over and over again throughout the years to invest in something new, we need to start looking at investing in something new today. It's just not going to handle the workloads of tomorrow without the processor efficiency and the gains in processor efficiency that we've historically experienced. So anyways, executing the plan. Let's talk about what it means to actually do it. Okay, I got 25,000 developers. They all know how to use a relational database. The reality is, no, they don't. Anyone who sits there and tells me, all my developers know how to use a relational database, why don't you go talk to your DBAs who are fixing all that broken stuff when those applications scale? Then you're going to find out who actually knows how to use the database in your organization. The reality is, developers know how to hack the relational database, okay? You can hack the NoSQL database too. but you get in a lot more trouble a lot faster with the NoSQL database because there's no, lack of ad hoc query support and the cost of ad hoc queries. So the reality is you got to know how to use the technology before you're going to have good results. And that's what these two charts are telling you. The one down below, that's the adoption curve. If you look at NoSQL today, we're still there in that early adopter phase, right? There's some sort of technology trigger. We talked about that in data pressure. It's about cost, right? It's either too expensive or it's too slow. And what we're going to do is invent something. And that's where the innovators come in. The innovators have some solution. Hey, we got this great database that scales. It'll fix all your problems. Everyone who's having that problem goes, great, let me go try this. And they have miserable results, right? They don't see the same results. We saw this at AWS. The first team to come in and talk to me at AWS about this was the shopping cart service, right? Shopping cart service had it's a very primary service for AWS, or for Amazon, obviously, and they came and said, we can't use NoSQL technology because it's too expensive, it's too slow. And what was really happening was they were adding items to the cart, and people use the shopping cart at Amazon really strangely, right? Well, not really strange if you think about it. They'll add a couple items to the cart, they'll add more, they'll go check out, they'll delete a bunch of items they don't want. It's like a temporary storage spot. Maybe they'll put them on the wish list or whatever, but if you think about what's happening on that shopping cart, right, items are being worked with independently of each other in the relational database. Those are just rows on the order items table. Okay, so it's no problem, just small little updates to individual rows. But the shopping cart team built a single document in DynamoDB, and they started adding order items into it, and that meant that the cost of each item you ordered included the cost of all other items in the cart, right, which made it more expensive. So their updates were more expensive. Again, the solution was to create a bunch of little items and tie them together with an index or onto the same partition. And this is the key. If you understand how to use technology, you're going to have better results. And that's what my team does. Okay, so what we did at Amazon was we spent our time initially working on kind of your traditional advocacy activities, right? We went out, we had things like this. I talked about the technology, look how great it is. Everyone goes excited, they go and start using it. We do workshops. They go, hey, this is fantastic. But when they walked out of that workshop and they walked out of our sessions like this, they say, hey, that was fantastic. I learned a bunch of stuff. But I didn't learn what I needed to know to fix the problem I'm working on. Right? Nobody told me that. They told me how to solve a problem. If it happened to be the problem they were working on, then great, they actually figured something out. But if not, they didn't really get much. So what we did was we changed up the script, and we said, okay, it's about exploring the data modeling, and to do that, it's more than just this. So we go in, I run these events, they're called MongoDB Day. We do advocacy like this for a day, for a half day. We talk about the technology. We introduce people to aggregation framework and things like this. But instead of workshops, what I do is for a week or two in advance, we have our marketing team go through the org and recruit teams to sign up for design reviews. So I'll run an event, like we ran one for a large international banking customer in Columbus. The other day, we had 500 developers on site. We ran 22 design reviews over 2 days. And I'll sit down with each team for an hour, me or one of my guys, and we just break down their access patterns and talk about their use case. And we produce a prototype of a data model that they can use to iterate on. Because what I found is that at Amazon was that developers are really smart. Okay? Developers just need to be shown where the path starts. Oftentimes, 90% of the time, that's all you need. But without somebody to show them where the trailhead is, they can spend a lot of time stumbling around in the dark trying to find it. Okay? So that's what my team does. We just kind of show them the path. Then they take that prototype of the data model and they'll go iterate on it. And oftentimes what they do is they come back and they say, hey, Rick, look at what I did. I didn't know if it's right, but what you told us was good, but we found this would probably work better for us. Honestly, I've learned everything I've learned from the teams I work with over the years because that's exactly what happens. They come back and show me something really cool. And then I'll put that in my quiver of arrows, so to speak, that I can use with teams I talk to again in the future. And that's really what has built all the design patterns that I have for NoSQL today are this myriad of access patterns that I've kind of come across over the years. I've literally at this point modeled over 1,000 workloads in NoSQL, and I can tell you there is not a workload out there that you cannot use for NoSQL, right? It is a general purpose database, especially when you look at the features of the developer data platform today. Very powerful platform for you. So if there's anything you can take out of my session today, NoSQL does not mean non-relational data. There is no such thing. Again, that's the noise between the stars. We don't care about that stuff. The ERD is everything. It still matters. It's going to define everything about the relationships in your data. It's going to tell me, it's going to inform how we're going to access the data, and it's going to inform the document model that we're going to use. The relational database, its day is done. All right, you can keep on pouring more money into it, but I learned in high school physics, anything can fly, right? Even a brick will fly with enough velocity, and that's the relational database today. Will it scale? Yes, of course it will scale. Distributed SQL is out there. If you think that distributed cross commits and Paxos and increasing the time complexity is somehow going to make you more cost efficient, then go for it, but the reality is it's not, okay? Time complexity is the enemy. We want to reduce time complexity. The only way you're going to do that is NoSQL. So it is a great fit for OLTP applications, and with the SQL Read API MongoDB has today, it's also a really good fit for your OLAP workloads as well. So that's the information I got for you today. I think we've got a QR code chart, maybe. Yes, we do. If you like this session, then this is the QR code that you can scan. If you don't like this session, then you can use the one from the last session or the next session. And then thanks so much for taking your time. I really appreciate it. Love talking to you guys. Thanks.